oscillations in a room temperature magnet Bose-Einstein condensate. And the first, I would like to present all our team who participated in this research. And research has been performed in 3 scientific organizations. It is in Kaiserslautern University, Germany, and majority of measurements have been done by our PhD student Oleksandr Serha and PhD student Helena Lysenko-Shmarova, developed together with Viktor Lvov and Anna Pomilov from Weizmann Institute of Science, theory describing these effects, which I will present today, and also the strong contribution to the development of experimental technique has been done with the third PhD student Pascal Frey. And the first idea should I give respect to Gennady Milkov, who was our presented this first idea of observation of Josephson oscillation, not in superconductors, but in magnetic materials. It was from Professor Gennady Milkov from Taras Shevchenko National University of Kiev from Ukraine. And all work was coordinated by a leader of our group in Kaiserslautern, by Professor Burkhard Hillebrandts. And I will start first from the idea of that media where we have observed our Josephson oscillations. And the first I should start from a magnet gas. And here you see the many magnetic moments, local magnetic moments, which are placed in some magnetic material. It can be magnetic isolators, it can be magnetic metals as iron or some alloys or Heusler compounds, and it's macroscopic magnetic moments which couple to each other due to the exchange interaction and due to the dipolar interaction. And you, as know, when external magnetic field is applied, they can process around this magnetic field, but due to the coupling, they process synchronously, and due to this appears some wave which you can propagate here from low left corner to the upper right corner, and these waves are described by eigenfrequencies and described by eigenwave vectors. And in the frame of the second quantization, it is now we can describe such classical waves, spin waves, we can describe as quasi-particles, as magnons, quanta of spin waves, which corresponds to one flipped spin of electron. And if you have, for example, parabolic dispersion characteristics of our wave, and it's possible if this wave mostly depend on exchange interaction, we can present energy in such a form where energy is proportional to the squared quasi-momentum, and eta here it is the exchange constant of our material, and we also quasi-momentum can present in such a form as h bar multiplied with wave vector, and also in such a form very well it can be defined the mass of magnet, which is here depends on the exchange parameter of our material. And the last I would say that our magnet has a spin 1. So we have spin 1 over 2 up, and after the flip of electron spin down minus 1 over 2, the total spin of our quasi-particles is 1. And it means that magnets are bosons with spin 1, and similar to other quasi-particles of such type and other bosons, real particles, for example, the magnets are described in thermal equilibrium by Bose-Einstein distribution, and here you can see this Bose-Einstein distribution, also very well known, where D is the density of states and mu is chemical potential. And this chemical potential in thermal equilibrium is 0, because particle can be created or can be thermally annihilated, and quantity of particles is not concerned, but depends on the temperature of our system, which is the quasi-particles. And here on the left side, you see the distribution of particles, where here we have the logarithmic frequency, here we have the quasi-particle density. I should attract attention that there is a minimal frequency in the system, and this frequency is not equal to 0, because we can change this frequency by application of the external magnetic field. So it will be a magnetic ratio multiplied with a magnetic field value. But if we will, in some way, change the distribution of these quasi-particles, In such a case, we can obtain the situation when chemical potential is not zero anymore, but will be equal to the frequency of the bottom of will be equal to the energy of the bottom of the spin wave spectrum. And in such case, we can expect formation of Bose-Einstein condensate. How this change can be done? There are a few proposed and tested methods, and one of them is external injections of magnets beyond the thermal equilibrium level. It is enough, as calculated, to inject approximately 3% above the thermal density of magnets, and it increases the chemical potential to the bottom of magnet spectrum and leads to the Bose-Einstein condensation scenario, even at room temperature. And this observation has been done still in 2006. And here, before I will start to present our results, I would show to demonstrate the spectrum of spin waves which we use. And here, this spectrum you see here in the center is calculated using Landau-Lifshitz torque motion equation. Here the change of magnetic moment with time, here magnetic ratio, magnetic moment, and effective field. And in this effective field included the external magnetic field, which we can apply with electromagnet, for example, field which depends on dipolar interaction between magnetic moments, and fields which describes exchange interaction with neighbor spins. And here. And as exchange interaction is long distance interaction, it means that its contribution increases with increase in wave number. Here in this area, you can see, and in this area in the center, the most influence on the spectrum of magnets is due to the dipolar interaction between them. And this spectrum calculated using the approach proposed by Kalinikos and Slavin, calculated for some specific case, it is in plane magnetized magnetic field. And this magnetic field is yttrium ion garnet, this magnetic oxide, non-compensating antiferromagnet. And why we use this? Because it's a room temperature ferromagnet, and we can work with room temperature. It's the first, is to observe Bose-Einstein condensation at room temperature. And the second one, these materials is unique. It has the lowest magnon damping of any known material. And why it is important? It is important that externally injected magnets in our system should live for a long time. We should work in quasi-equilibrium situation when quantity of particles is not changed. So the spectrum is very anisotropic. Dispersion branch along a perpendicular direction to the bias magnetic field when Q is in plane of our field is proportional to Q squared, is completely determined by exchange interaction. If spin wave or our magnets propagate along magnetic field, the dispersion branches, which are described by these blue curves, has a minimum. It's minimum because the increase is due to the exchange interaction, but decrease due to the dipolar interaction. And that is why at the sum value of wave numbers, there is energy minimum. And in these positions, for minus k and for plus k, it is expected to have Bose-Einstein condensate. How can we inject magnets in our system? We use in our lab parametric pumping. It's principally very known situation. It's used in the optics, it's used in electrotechnics. One photon splits into other particles. And here you can see the photon, its doubled frequency respect to the desired magnets, splits into quasi-particles with minus k and plus k in order to conserve momentum in our system. And also the ratio of frequencies depends on energy conservation law. And so parametric pumping by electromagnetic wave at microwave frequency, approximately 14 gigahertz, is used to inject magnets in our system. But it still doesn't change the chemical potential. In order to change chemical potential, magnets should thermalize. And equilibrium, quasi-equilibrium should be reached in our system. Thermalization develops very fast. If we inject a lot of magnets, density of magnets is high, probability to scatter is high, And thermalization time is approximately 10 nanoseconds, if the lifetime is a few hundreds of nanoseconds. And that is why magnon thermalized due to particle scattering processes and incoherent, overpopulated magnon gas is created. And if density of this gas is high enough, we can observe Bose-Einstein condensation at minus k and plus k positions at the minimum of the magnon spectrum. How we can observe this? It is normally done using the brilliant light scattering technique. Why? Because the wavelength of these magnets is approximately a few micrometers, and it's a challenge to observe them using, for example, some inductive antennas or something as this. And that is why we radiate our sample with laser light, and this laser light scatters on magnets with annihilation and creation, and after that we see in spectrum of scattered light, Stokes and anti-Stokes peaks, the intensity is proportional to the density of magnets which we analyze. And here you see that we have a frequency resolution in such case because we can analyze our spectrum in frequency. But this frequency resolution is not very high. It is approximately 50 megahertz. And wavelengths of our, not wavelengths, waveline width of our magnets due to the long lifetime and natural decay to the lattice, to the phonon best, is approximately 1 megahertz. That is why it's not possible to understand if we really see some single state as it's necessary for Bose-Einstein condensate. And we see that a majority of magnon states are within of the resolution bandwidth of our setup. And in order to resolve, we introduce the additional, to resolve this wave number uncertainty, we introduce the additional wave number resolution in our system. And it can be done by changing of the direction of the probing laser beam. And in such a case, with such a setup, we can change the direction of the probing laser beam and determine which wavelengths of the spin waves we observe, as it will be exactly two wavelengths, two wave numbers of probing light multiplied with the cosine of probing angle of our laser beam. So, and we can have very good wave number resolution in approximately 1% relative to the maximal achievable wave number in our system. So let's look on the results, first results of the experiment. If we have something like this, when we have our dispersion, this point, orange point, indicates the position where the Bose-Einstein condensate of quasi-particles should be formed. And let's analyze only this part with wave number resolution. And we will apply pumping pulse, first indicated by this in time, here the wave numbers. And we pick up the signals only from the bottom frequency, at the bottom frequency. We see that when we will apply external microwave pumping pulse and start to inject magnets in our system, the first magnets populate only these higher values of wave numbers. And no one, it's extrapolated, very small density of magnets appears at the minimum of the spectrum, and there is no concentration, no Bose-Einstein condensation at all. But what occurs when we will switch pumping off? When we switch pumping off, we see that magnets which previously occupied states at high Q numbers, they will propagate to the global energy minimum in our system and form here the dense peak of magnets, and which we associate with Bose-Einstein condensate. So it means that BC is formed after the pumping is switched off. Why? Because pumping magnetic field disturbs the system and destroys the coherency in the system. And it means if we would like to investigate some behavior of these Bose-Einstein condensate, we should analyze this freely evolving magnon BC when pumping pulse is switched off. Bose-Einstein condensate at the bottom is formed. You see this formation of the peak, this dense peak, and after that there is decay, there is a free decay. You see linear, it is exponential, but in logarithmic, in the logarithmic scale, it is linear decay of our magnets. And what kind of properties of Bose-Einstein condensate we would investigate? For example, something what is normally related to the properties of condensate and superconductivity, some type of superconductivity, supercurrent in magnon BEC. So supercurrent flow of particles due to the phase gradient of the condensate wave function. And if the complex BEC wave function of particles can be presented by this formula, where the particle BEC density Np is the squared module of this complex function, and particle BEC phase can be here also found. Supercurrent of particles normally determined by this formula, where the mass of particle, density of particle, and also phase shift in particle BEC, in phase of BEC wave function. Complex BEC wave function of magnons is described by this formula. It is as a plane wave, plane macroscopic wave. And magnon BEC density and phase described by the complex amplitude here also. And if we will assume some continuity equation for this for density of our magnons, and we can assume this for some not very long time intervals when density of magnons can be assumed to be conserved, we can write this continuity equation, present this continuity equation, this change in the density of particles as change in the squared density of module of complex amplitude. We will obtain this very simple formula. Yeah?
2 minutes.
Okay, so I will be faster. So after that we will, using Gross-Pitayevsky equation, here's the dispersion coefficient, and continuity equation, we can obtain the formula for the quasi-particle flux here. And if we will stay in the minimum of our spectrum, here the group velocity should be cancelled out. And as a result, we obtain the formula for magnon supercurrent, where here instead of mass stays the dispersion coefficient, density of particles, and change in the phase. How can we change phase? We can change magnetic field. If we change magnetic field, we change frequency of our condensate, and with time, we will have accumulation of phase. So by changing external magnetic field, it is possible to control the frequency of phase of the magnon BEC. And we have done this. In addition to the application of microwave field from the microwave pumping generator, we applied to some metal wire on the surface of our yttrium-ion garnet film, we applied DC current. Magnetic non-uniformity, TREDGE, it is magnetic well when local magnetic field decreases as on the left picture, or ridge wall when it is increases, can be created by change of polarity of this current. And in such a case, we have a few zones. The central zone, when we apply current, when the minimum of our field, it is a trench, and we have right and left zone, where Bose-Einstein condensate described by the undisturbed bias magnetic field. And so, the frequency of Bose-Einstein condensate in central zone, left and right zone should be different. Phase will be accumulated, and so supercurrents will flow from right to the center and left to the center and in opposite direction. And we measure the density of particles in the central zone. If it is right what I told, the density should oscillate. And really you can see that when pumping is switched off, the first peak formation of condensate appears, and after for some negative current, when magnetic well is created, we see the appearance of oscillation. And it is interesting when we create a magnetic wall, magnetic ridge along this structure. There is no oscillation for any applied currents. But if you will apply negative current and create well, you see how with increase in the current and the depth of the well, oscillation appears in our system, which we associate with AC Josephson effect in a magnon BEC, which is carried by room temperature ferromagnetic field. Principally, this density of condensate is distributed around the central zone non-uniformly. You see that the most density initially is on the left, on the right side. We assumed this in our solution of Gross-Pitayevsky equation with this dashed dotted dotted line demonstrates the initial distribution of condensate. And after that, we calculated how this condensate evolves. And you see this, there is in the center of this red zone, the oscillation of the density of condensate. After performing Fourier transformation, we can find some carrier frequency of this oscillation. And this frequency depends linearly on the trench depth. And you see this dependence in our calculation. And it's interesting that if you will determine the position of peaks and calculate the frequency of oscillation in experiment, you see that frequency of the Josephson oscillation is also described by linear function and a good prediction with a theory. And so I can go to the summary and say that AC Josephson effect in a magnon BEC was observed. The appearance of the Josephson effect is manifested by oscillation of the magnon BEC density in the trench caused by a coherence phase shift. And advancing of the physics of room temperature macroscopic quantum phenomena for their application in magnet supercurrent, super spintronic devices is obtained from these experiments. Thank you very much for your attention.
Thank you. It's interesting that magnons can go to BEC at room temperature. But my question is, how this condensation is reflected in magnetization Q? That is, the dependence of magnetization is on temperature. What happens at critical temperature for magnetizations?
I should say something. Magnetization principle is not changed because you see that the system not changed in general. However, if you will assume that some dipolar magnons, some magnetic moment of a dipolar magnon is different than magnetic moment of a pure exchange magnon, some small variation in magnetization is possible. But it is small variation, it's out of our experimental abilities. So if exchange magnons moves to the bottom, magnetization should a little bit decrease. Because some angular moment will be passed to the magnetic field from magnetization.
Oleksandr, may I just ask you your vision? So could you imagine some further experiment concerning the Josephson physics? For instance, if you have a phase as a tuning parameter via the change of the applied magnetic field, for instance, if you would add some AC component of the field, would you expect to see some interference effect similar to, for instance, Shapiro steps in non-Josephson response in superconducting systems?
Principally, yes. Yes, and also it is one direction. Thank you very much, it's very interesting question. And we working in such direction. Another one, it is, I should say, if you look here on this figure, where supercurrents is indicated, I should say that these Josephson junctions between left and right and red zone, between right and central zone, they are not traditional. There is no, should I say, tunneling in such a case. It is due to that fact that our difference in potential energy doesn't produce some macroscopic current of magnets, as it is, for example, as macroscopic current of electrons. That is why, in order to support the difference in the potential energies of our condensate in left, for example, and in central zone, it's not necessary to have a tunneling or a weak contact. And we would like to also to observe the experiment with a weak contacts, which are also possible, and to have not a gradient in the potential energy, but more or less sharp step, and after that also to combine this with this Shapiro steps experiment.
Thank you, Oleksandr, for the great talk. So my question relates how important it is in all these experiments to have macroscopic. So my question relates how important it is to have macroscopic quantum state in all these experiments. Imagine that we don't have all magnons here sitting in the same wave function, but another kind of condensate when we can speak about some delta omega and delta k of the condensate. Would you still observe these oscillations in the experiments? If it would be.
I'm very sorry, connection was broken. Maybe we will discuss, if there is not enough time, we can discuss the last question in personal communication.
Okay.
Or if you can repeat, because I simply I didn't care.
Okay, let us discuss later then, Alexander. It's fine. Thank you.